in this case, what happens is that the attacker is not really trying to override its structure the way that we talked about so far, right? And the reason is very simple, because the code I showed you kind of looked contrived, right? So it doesn't really look like this is the most likely piece of code that somebody can write. And so the likelihood that the attacker will find that type of code and be able to exploit that, the probability is quite low, right? So that's why you're not going to find that many real-world instances of the attack that we just talked about, right? But instead, there is another type of attack which is called, which involves overwriting the heap metadata. Okay, so let's look at how this thing looks like. Okay. So the attack relies on how heap blocks are stored in memory. Right? So there is a heap management routines. They need to sort of keep track of what are all the free blocks in the heap. Right? So when you ask for a new memory block, the heap management routines have to say, hey, here is the first element from the free list, or here is the 10th element from the free list, and they give it to you. Okay? So in order to do this, the free list is typically kept as a doubly linked list. Okay? So think of what happens in a doubly linked list. So we can write a heap block, represent a C heap block as a structure in C. Okay, so we can say okay, so so you can define it as a C structure. The only thing is that, okay, I call it 1 byte data. That's not really what I mean, right? So what you do in C is, if you want to have a variable size structure, one common convention is that you declare it to have a size of 1, and then when you allocate this block, you're just going to make it however large you want. Okay? So ignore this, but basically, so let me not confuse you, and let me just say, okay, this is an array. We don't know exactly how big it is. Okay, we'll assume that, okay, that we'll do the sensible thing with this data. Okay, so so you can say, let us say this is part of this is a free block, okay, and the program asks for some amount of memory, and the heap handling routine is going to come back and say it wants to it allocates this block. Okay, so the free list is going to look like this, right? So there is the previous pointer. It's going to point to that. and so on, right? So this is how these free blocks are going to be kept in a doubly linked list. Okay? So now, what this program does is, let's say it wants to take this and return this to the program when it requests a free block. Okay, then it's going to, the heap management routine is going to basically delete this from the free list. Okay, so how will the delete look like? It will look like, let's say current is the name of the block that it wants to, the heap management routine wants to return. So what it's going to do is it's going to say current arrow previous arrow next equals, just make sure C's backward pointer is right. Okay, yeah. So essentially what happens is that it's going to say, okay, if I want to delete myself from this list, what I'm going to do is I'm going to go to the previous block and I'm going to update its forward pointer to point to my forward pointer. Okay, so that's, so current, I'm going to go to my previous and I'm going to set the next of the previous to be my next. Okay, now this looks perfectly reasonable, right? So when you look at this, it's hard to see that there is actually some kind of a vulnerability or a bug in this piece of code. Yeah?
Why aren't you reassigning the previous of the next as well? That's the problem, okay.
No, that's not a problem. It is just that this one is complicated enough, and we can find the problem with this one update. The other update is kind of similar, right? So, so it all looks reasonable, except that if the attacker controls, if the attacker has somehow managed to override these fields, okay? So then, let's say the attacker so let's say the attacker wrote A over here and B over there. Okay? Then the effect of this is it's going to interpret A as a memory address. Okay? And then it's going to write this value. Okay, because this is, remember, this is next. Right? So this is previous and this is next, right? So what this is going to end up doing is it's going to interpret A as some memory location where something is going to be written, and B as the value that's going to be written there, because again B, this is nothing but B, right? And this is A, right? So it's essentially A arrow next, which if you look through exactly how it gets translated into machine code, it's going to be something like, it's going to take A plus some offset, okay? Which is going to be, in this case, it's going to be 8 bytes from A, okay? So what it ends up doing is, it's going to, if the attacker writes A here and B here, then when this free operation happens, the free routine ends up writing B at the memory location A plus 8. Okay? So essentially, the freeing routine gives the attacker an arbitrary write into memory capability. Okay? The attacker can basically choose A and B and then they can have the value be written at the memory location A plus 8. So in the example here it says 12 because the example uses a particular implementation of heap management where the next field is actually 12 bytes in and not 4 or 8 bytes in. Okay, it's just particular the details of a particular doubly linked list that they are exploiting. Okay, so this is sort of very interesting because the attacker doesn't really have to find a particular structure which has a function pointer inside it and so on, right? So all they have to do is they simply overwrite the heap metadata, and when the heap block is dequeued by the heap management routines, then the attacker is magically able to write some value into some memory location. Okay, so in your assignment, you will have an example of this. So you'll be given a particular implementation of heap management routines. Okay, I made it. It's meant to make your assignment simple. So it is actually a very, very simple heap management routine, which I think probably takes like 50 lines of code or something like that. So you can easily look at it and understand what it is doing. And then the vulnerability in there basically allows the attacker to be able to override arbitrary memory location with an arbitrary data item, right? So this is it's good to think about it this way because there are a lot of details about the exploit, right? But if you just get lost in in those details, then you will not be able to think about the next step, right? So it's better to sort of say, hey, I have a vulnerability that gives me a particular capability, right? The ability to do something. And then I'm going to use that ability in crafting the rest of my attack. So for instance, in this case, what the attacker wants to do probably is to find some function pointer in the program and override that with some value, presumably the value that points to attacker's code, right? Because this is again allows the attacker to do control flow hijack by essentially providing the location of their code in B and choosing A so that this will target a particular function pointer that already exists in memory, right? I mean, it could even be a return address, right? So A could also be a return address, or this could target any function, any code pointer. So as long as the attacker knows the location of the code pointer, then he can target the code pointer. Okay, so that's you can see the at your leisure you can look through these slides, or you can instead just do your assignment. Again, many parts of your assignment will be optional, so you may or may not decide to do this. But if you decide to do this, then of course you'll understand this in all its coding, right? Gory details. Okay, good. So as I said, heap overflow, to summarize, it provides a primitive to write an arbitrary 32-bit value at an arbitrary location. Okay, I say 32-bit because we are again talking about 32-bit instruction set in 32-bit architecture. If instead you are going to do this on a 64-bit processor, then of course these would be 64-bit values. So the attacker can target any code pointer. They can target a function pointer, such as the return address on the stack, or a GOT or a global offset table contains basically the way dynamic linking works in Linux, right? So dynamic linking means your program calls certain functions in certain libraries, but these libraries are not part of the executable, right? So they are not being included in the executable. But instead what happens is that at runtime, the system loader will load the program, load your executable, and then it will load all these required libraries at runtime. Okay? So when that happens, somehow when your executable makes a call to this library, right, then that particular call has to be resolved, right? Because if it was already part of the executable, then the compiler or the linker would have replaced the call with the address of where that function is located, right? But if the function is only loaded at runtime, then until that library is loaded, you don't know exactly where that function is. So in order to make this work, what happens is that there is a table that is used where what the program, the executable, will do an indirect call using this table, okay? And then the linker, the dynamic linker, is then responsible for filling in the table, okay? And the details are not that important. The point is that all calls to standard libraries will go through this kind of a table, and the attacker can target that table and overwrite the function pointer that is in that table, and that's another way for the attacker to take over. Okay. The attacker can also target, data pointers like file names. So instead of, let's say your program already executes some program. Okay. Now the attacker can make it execute a different program by simply overwriting that variable. Right? So if there's a string name that represents the name of a program that your application is going to execute, by overwriting that string, the attacker can have some other program execute. Right? So again, there is a lot of variability in terms of what the attacker really wants to do and can do. So depending upon that, the attacker may also target data variables. So that brings us to the question of, okay, suppose what can be done to deal with these attacks? Right? So one of them is what is called a heap canary. So just as the case of the stack, you can use heap canaries in between a buffer and the metadata. Okay, so where is this, buffer? So typically, what happens is that you have the memory broken up into a bunch of these heap blocks, right? So what happens is that immediately before the heap block is another heap block, okay? Or think of, so here is one heap block, right? It has its data field, and here is another data heap block, and it has its own data field. And now what happens is that if there is an overflow past the end of this heap block, then it will end up overwriting the metadata of the next heap block, right? So this is how the attacker first, we said the attacker overwrites with B and A. How do they overwrite? By essentially taking this one and overflowing past the end of this into this. Okay. So one way to prevent this is by putting a canary over here. Right? So you can put a canary between the buffer and the metadata that you want to protect. Okay? It doesn't have to be in this particular design. The canary has to be at the beginning, but you can imagine that there can be other implementations where the data occurs at the beginning, and then the metadata may occur at the end of the block. In that case, you would put it in the middle of that, in the middle of the block, right? So the canary has to be somewhere between the buffer and the metadata that you want to protect. Okay, if you do that, then the attack can be detected, and this is implemented into the heap today. Okay, so this sort of overwrite arbitrary location with arbitrary data, that's not something that can easily be done anymore. Okay. There are also various other things you can do. For instance, you can say, the problem comes only because I put the data and the metadata in one place. I'm going to sort of separate them and not house the metadata immediately after the data. And that's, in general, a good principle. Don't put control data and non-control data in the same place, because the non-control data is really the data, and that should that's bound to be populated with untrusted information, and you don't want that to somehow corrupt control data, because control data shouldn't be under the, something that any attacker or any untrusted source can control. So that's something that you can do, but it's not something that's widely deployed, because in real systems, right, you always have to consider security against performance, right? So if you separate the metadata, then there are some drawbacks. One of them is that you will need more storage, right, more memory in order to, for the same usable amount of heap space, the overhead for metadata will be much higher if you separate the metadata from the data, and therefore the more common solution that you will see deployed is